integrate over this surface, you get the total magnetic flux within this loop. Okay, then you can find the induced EMF, which is a voltage. Yeah, EMF we know electromotive force. Okay, is a voltage. Yeah, you can find induced voltage by differentiating the total magnetic flux enclosed within the loop. Okay, by time. Okay, so you can imagine. Yeah, if the total magnetic flux within the loop does not change with time, you differentiate a constant, you get zero, yeah? So no induced EMF, no induced current. Okay, no EMF, no current, yeah? So this magnetic flux within the loop must change with time. Okay? If it doesn't change with time, you have no induced EMF. Okay? If it changes with time, then you get your induced EMF, yeah? And it's the negative differential of your total magnetic flux within the loop with time. Okay? So this is your induced EMF. Okay? If you have one loop, you just integrate it over that surface area and then you differentiate it with time. Okay? If you have n number of loops, just multiply it by n times. Yeah? Okay? Now, then the next one is Lenz's law. Yeah? So we say that an induced EMF is there. Okay? If an induced EMF is there and you put a resistor there, okay, then there will be a current flow. Yeah? Induced EMF and then a current flow. Yeah? In which direction this current will flow. Okay, Lenz's law tells you that it tries to oppose the change of magnetic field. Okay? So we see that, for example, in this particular case, your magnetic field is flowing into the board. Yeah? Inside the loop, yeah? Don't look at outside the loop, look at only inside the loop. Okay? Because the induced EMF is due to the magnetic flux only within the loop, yeah? Not outside the loop. Okay? So if we look at the magnetic field within the loop, okay, this one is moving inwards, yeah? If it starts increasing with time into the loop, Lenz's law says that you have to oppose this increase, yeah? So you have to reduce it by inducing a magnetic field in the opposite direction, correct? Yeah? So if you induce a magnetic field in the opposite direction, right-hand rule tells you that the current will be the green line, yeah? Counterclockwise. Okay? Now, if it's decreasing with time in this direction, okay, then you have to induce one inside and it will go in this direction. Yeah? You have a lot more practice. Yeah? 3 practice in this particular tutorial about this. Yeah? Okay? Now, another thing I need you to notice, yeah? Okay, if you do your practice questions online as well, you will see this as well, yeah? Now, if they have a resistor here or whatever, voltmeter here, okay? And if they label it plus or minus, okay? Current always goes from positive down to negative, yeah? Okay, so if this is your resistor, this is the plus N, this is the minus N, current flows in this direction from positive to negative, yeah? If you find that your current is flowing in the opposite direction, put in a negative sign, thank you, yeah? Okay, please remember that, yeah? Okay? So we start off with the first tutorial question here, yeah? Okay, on the tutorial 5. Okay? Now, we have a rectangular loop. Okay? This rectangular loop is drawn over here. And it's shown in figure 1. It lies on the xy plane. Yeah? Okay? First question, yeah? Z-axis pointing in or out of this board? Stanley. Z-axis is pointing in or out of the board?
Out.
Everybody agree out?
Yeah.
Yeah? Okay. Again, yeah, right-hand rule. X cross Y gives me my Z-axis, yeah? It's pointing out of this board, yeah? So the Z-axis is pointing out of this board, okay? And it says that there's a magnetic flux density B, okay? It's 0.3 T in the negative AZ direction, yeah? Negative AZ you can see, yeah? It plays across, meaning it's flowing into the board, yeah? Okay, negative AZ direction, yeah? Determine the voltage V1 or and V2, okay? Across these two, okay? So, now, looking at this, yeah, okay, we can already determine whether V1 and V2 is supposed to be a positive number or a negative number, correct? Yes or no? Yeah? Okay. So, magnetic flux density, yeah, it says it points in the negative AZ direction, and as time increases, it's going to change. Increase or decrease?
Should be increasing.
Increase into the bar, right? Yeah? Okay. So if it increases into the bar, you expect your current to be flowing in the clockwise or counterclockwise based on Lenz law?
Counterclockwise.
Counterclockwise? Yeah? Okay. So this is going to go in a counterclockwise. Okay. So your current goes from positive to negative. V1 and V2 will be positive value. Yeah? Okay, remember that, yeah? Okay, so we're going to start working on this question, yeah?
Asal?
So, now,
Because it's induced like
Increase.
yeah, induced is like terbalik lah.
Yang oppose dia change.
Yes.
Opposing dia. Aku
Yes.
cakap decrease sebab the number is getting bigger because of the minus
Buat
sign.
aku tak faham.
So it's going down. Minus negative what? Come on lah.
Minus is dia punya direction je.
Direction. I correct. Cuma salah direction.
Kau tahu kan korang ni suara semua boleh dengar
salah
kan?
direction.
Solat salah direction. Itu dah besar.
okay, so this is your magnetic field, yeah? It's coming here. Still not here, huh?
Ni satu ni dua sama. Ni dua sama ni kau.
Ishak.
Isa. Anak Isa.
Asal kau pegang
Mana botol-botol dah tak mana? Anak ah. Tadi tak nampak, tak clear.
Kunza,
Fine lah.
Pegang kan?
you just came in to do the question. Very good. Thank you. Okay.
Panjat
Okay, sit down first. Stop. You haven't done
The V
yeah. So you're supposed to find the flux first, yeah? Okay. So Sub is going to find us the total magnetic flux passing through this rectangular loop, yeah? He's going to do that by integrating the magnetic flux density over this surface area, yeah? Vector. Yes. So to integrate over this rectangular loop, yeah, you integrate in the x direction and the y direction, yeah. So b, you can write that down, is minus 0.3 t in the az direction. Okay, ds is, you just told me, you integrate in the dx and dy, yeah. And this surface is pointing in which direction? Okay, yep, good. Yeah, yeah. In that direction. Okay, good. So, say for example it goes from 0 to x, you don't know what value, and 0 to y, yeah? Okay, then what do you get? After you integrate, you get minus 0.3 t x and y. Yeah? Very good. That's all. No. These are not integrated. Okay. That's it. Okay. Good. Thank you. Okay. Let's see what Sub did, yeah? Okay. He says that the total magnetic flux flowing through this area here is equals to the integration over that area, the magnetic flux density, yeah? Okay, the magnetic flux density, he says, is given by minus 0.23 t in the AZ direction, And he's going to integrate in the x and y direction, yeah, to get the surface area of this rectangle. So dx dy, and he says that this surface dx dy is pointing a vector perpendicular to this surface is in the z direction. Yeah? So you have the vector az over here. Now az dot az you get
1.
1, yeah? Okay, so you get a scalar value here, yeah? So when you integrate 0.3, negative 0.3t in the x and y direction, you get x and y, yeah? X times y is equal to
X times Y
area, which is equals to
4 meters.
4 meters squared, thank you. So this one, we know that it's equal to 4
the
meters
loop of
squared,
the
that's
area.
given in the question, yeah? X times y is 4 meters squared. And so we will have a total flux of minus 1.2 t. Yeah, that's it. Yeah, okay, minus 1.2 t. Yeah, okay. And then to find the induced EMF, what do you do?
Take difference
Minus
negative
the
difference of
flux
magnetic flux
over time.
with respect to time.
Okay, this will give you
1.2.
1.2 volts, yeah? Okay. So 1.2 volts is the total voltage across this rectangular loop, yeah? So if I want to find the voltage V1 and V2, how do I do that? Abbas?
Ketawakan orang lagi.
Different series.
You have 1.2 volts across these two thing, right? 1.2 is V1 plus V2, correct? I know that V1 plus V2 is equal to 1.2 volts, yeah? Because that's the total EMF across the whole loop.
Oh,
Okay.
yeah. Yes,
Ah,
yes,
voltage
yes.
divider.
Why
How do you
Abbas?
do that?
Yeah, correct.
V1 is equal to,
V1 is
yeah? This one is 2
4
and this one
over
is 4.
6 ah.
So it's
4 over 6 times 1.2. 2 over 6 eh? Oh, tu current eh?
times 1.2.
Tu V1 tu, kata V1.
So he says using
Oh,
potential
V1 to
divider,
1
2
to-
ohms divided by 2 plus 4, yeah? 2 ohms plus 4
Oh,
ohms,
V1
that's
yang
the
belakang
total
kan, eh?
resistance. Multiplied by 1.2, you will get 0.4 volts. And V2 will be the remaining, which is 0.8 volts, yeah? Okay, and to indicate the direction, you make sure you write that V1 is a positive value and V2 is also a positive value.
Value.
Yeah? Okay. If it's in the other direction, put the negative sign in. Yeah. Okay. Again, despite the fact that your induced EMF is this negative differential of your magnetic flux density, it doesn't tell you the direction. Yeah. Okay. The direction you still have to work it out yourself, and then put in whether V1 and V2 are positive or negative. Okay. In this case, we know that the current is flowing in the counterclockwise
Current dia
direction.
dekat.
Okay, and therefore it is positive
Oh, dia punya
0.4 volts
dia
and positive
positif dan negatif kat board dia
0.3
salah.
Yeah.
Terbalik. Oh, no,
Question.
no, the positive and negative of your V1, V2 on the board different than the
Different.
that's it je. Class participation je. Tu je.
Plus and minus, yeah? Plus and minus. Good, huh?
Oh,
Thank you.
okay.
Okay.
Pasal dia compare cause induce
So the current
this
is
one is
flowing in the
increasing
counterclockwise
is
direction. Okay,
tapi
so
bila
it
kau
goes
nak
from
induce
positive to negative, V1 and V2 are positive. Any other question? Any other mistake on the board? Okay?
tapi yang EMF yang negatif dia negatif EMF kan dia
Which
letak
one?
1.2 is because oh dia punya 1.2 dia negatif
Differentiate ada negative sign dia tak ikut.
ikut ke? But kau differentiate dah memang negatif so negatif apa dia? Oh korang ambil